A very warm welcome to everybody this afternoon to our second week of the 2021 summer school with our bite-sized corrosion. It's really lovely to have everybody join us again. We do hope that this afternoon will spark an interest in you, something that perhaps you've not known before. I said this is the second week. Last week we looked at both the topics of SIPs and DCVG surveying. And if you would like to catch up virtually on those topics, you're welcome to sign up free of charge on our Teachable platform, where you can find past discussions as well as the first two sessions from this summer school. Now, during this 2021 summer school, we've been focusing on some of the non-intrusive close interval pipeline survey techniques. Last week, as I said, we spoke about close interval potential surveying, and we spoke about DCVG surveying and how DCVG can be used to find and locate defects in our pipeline coating, whilst the SIP survey tells us about the operation of the cathodic protection system itself. Today, we'll discuss the PCM survey, and we'll follow that tomorrow with a discussion on ACVG. And as usual, I have Neil Webb here with me to discuss these topics. Just like politics, the cathodic protection industry is full of acronyms. I like to call it alphabet soup. And so we've picked our next acronym, which is PCM. And Neil, I'm going to ask you please to explain what PCM is. I thought it was a trademark.
Vanessa, well, I had a look at the definition of PCM, and there are something like 143 listed definitions for the term PCM. So when you see a bill of quantities in a pipeline inquiry that requires a PCM survey, you can be forgiven for not really knowing what to do. If you were a petrol head, it would represent a powertrain control module. If you're an IT guru, it would be a pulse code modulation exercise. If you're a bean counter, it'll be a professional credit management operation. And if you're a pipeline operator, then it stands for the pipeline construction manager. So how the pipeline construction manager is going to survey himself, I'm not quite sure. But anyway, PCM is also the trademark of a company called Radio Detection, and they have developed a piece of equipment that they call the pipeline current mapper. And that's what the PCM stands for. So I want to acknowledge Radio Detection in this presentation. I have used some of the illustrations from their brochure, for which I thank them. And I hope that you will, as a result of this discussion, have a better understanding of what the pipeline current mapper can do. Now, we can't go into absolute detail in this because we only have 20 minutes, and the operation of the PCM equipment is quite complex, but the principle itself is very simple. The point about the PCM is that it measures the current that is actually flowing in the pipeline by means of a detection system. So last week we were talking about potentials and voltage gradients, and those needed contact between the equipment and the soil. And that contact was provided by wires and reference electrodes and things like that. The AC attenuation systems, which essentially is what the PCM actually is a non-contact survey technique. So we have a transmitter which injects a signal into the pipeline, and then we have a receiver which can measure the magnitude of the current that is injected into the pipeline. Now, the PCM stands out because the signal that it injects is a very, very low frequency signal, something like 4 hertz. And it tends to behave very much like the DC that we get from a cathodic protection system. And the beauty of this operation is that you can follow the current using a non-contact method, And you can also get a good idea of what's going to happen with your cathodic protection current. Whereas the higher frequency AC systems suffer from the challenge of attenuation along the pipeline, and the signal is dissipated as a result of the pipeline's impedance and capacitance and so on, whereas this PCM signal tends to operate more like DC. So in this photograph, what you're seeing, with this illustration, what you're seeing is the magnitude of the current in the pipe that has been registered by the detection equipment. And in this particular case, these points would be probably several kilometers apart, and it shows a pipeline where the current is being uniformly discharged or absorbed through the coating. And as you get closer and closer to the transmitter, so the signal increases in magnitude as you get more and more current being absorbed through the coating system. The transmitter itself is a fairly hefty chunk of change and a fairly hefty chunk of equipment, I should say. It's not your average piece of equipment that you would use for going treasure hunting and metal detecting. It's a powerful piece of equipment, and this then injects the signal into the pipe, and the operator then goes along with a detector that is placed over the top of the pipeline in order to measure the strength of the signal that is actually in the pipe. And it is important to notice in these pictures that the equipment is actually in contact with the soil only in terms of being physically stable. And the reason for this is that this bottom section of the equipment is a magnetometer, a very sensitive detector, and it needs to be absolutely stationary so that you get a realistic signal. It is not actually making contact, electrical contact, with the ground itself.
That's very interesting. So I'm essentially using the PCM to measure the signal, and I could have done that because it's a current measurement if I'd excavated the pipe and used a giant Swain meter, which is extremely impractical. So this does seem like an easier method. Is the PCM the only device we can use for inline current measurement techniques, or are there other devices, Neil?
It's probably the most commonly used device. There is another piece of equipment known as a C-scan, which has been around for quite a few years, and that works on a similar principle, but it doesn't have the same low frequency characteristic that the PCM has. So it is more of an AC attenuation piece of equipment, and it doesn't have the quasi-DC characteristic of the PCM equipment.
Last week we spoke about DCVG. Does the PCM survey tell us anything about coating defects either?
Well, yes, it does, in that if you lose current through a defect, and be that a coating defect or a foreign contact or whatever, the PCM will pick it up. But it does not have the same precision that we have with the DCVG, which, if you remember correctly, we're saying that the DCVG is a very, very precise locator of coating defects.
So what else can we use inline current mapping to do? If it's not for defects, what are we pumping current through our pipe to find or looking for?
Well, I think the primary purpose of this particular piece of equipment is to characterize the current flow in a pipeline. And it has the advantage that when you have a well-coated pipe, you actually have very little loss of signal through the coating of the pipeline. So if we have a look here, we've got the transmitter, and if this was a perfectly coated pipe, you would find that the current flowing in the pipe was pretty much the same over a large distance. So the PCM allows you to measure the current flow in the pipe and get a broad overview of the condition of the pipeline, and then you can say, well, this 5 kilometer section is good, the next 5 kilometer section maybe not quite so good, and then you get another section where there's no attenuation and so on. The advantage is you can get a quick overview of the condition of the pipe without having to walk along the pipeline route. You can go to road crossings, for example, if you're going through a highly congested area, and you can measure the inline current from the PCM at each road crossing and say, well, okay, from the previous road crossing to here is all good. So I don't need to worry about going in to do any more intensive surveying.
So almost like a first look. This would be
very
quite
much so.
a good quick.
Yes. The example here shows you that here we have a defect. Now, this defect could be a coating defect. It could represent a quite a wide area of poor coating, or it could be, for example, a foreign service contact, which is similar to a coating defect in that it causes an unwanted current drain on the pipeline. And you can see that in this situation, you have a significant change in the current level in the pipeline from 20 milliamps on the right-hand side of the picture to 700 milliamps on the left-hand side, showing us that we've got a significant loss of current in between. And that would equally be a significant loss of cathodic protection if we were looking at a cathodic protection signal.
So this would have tremendous value for trying to figure out where we have current loss.
Correct. And it's not only defects in the pipe. A lot of times we don't know where the pipe is going, particularly if you're talking about pipeline networks. And if you want to find out where is the current from the cathodic protection going, or why do I not have protection? What's happened to my current? This equipment really comes into its own. So for example, here, the transmitter typically would now be located at a cathodic protection injection point. So you switch the cathodic protection system off and you attach the PCM transmitter in place of the cathodic protection system, possibly even using the cathodic protection ground bed as the earth. That's this point over here. And then you measure the current strength in the pipeline. And you can immediately see if we move out from this transmitter, on the left-hand side, there's very little current. On the right-hand side, the majority of the current. So we know that the current is traveling on the right-hand side of this pipeline. And if we follow this pipeline route, if you were to go along here and assuming that you think that this pipeline just goes straight, well, yes, it goes straight, but when you get over here, you find that there's no current flow. Where's the current gone? So then you start scouting around and you can pick up the current at this point here. Or if you knew that there was a pipeline network, you can go and measure this just like you do using Kirchhoff's law in an electrical circuit. You know, current in equals current out. And therefore, you can say, well, my biggest issue now is actually on this branch. And if I follow the branch, you can use this to actually trace the branch. So maybe this was a pipeline along a road, and the branch goes under the road and off through a factory development on the other side. And you can follow that pipe and follow it through. And if you come here, and this defect effectively could well be, say, a non-functional insulating flange on a gas distribution network where the pipe goes into an end user. And you could say, oh, okay, that's where I need to go and do my maintenance work in order to repair the system so that my cathodic protection system can function as it should. So it's a really, really powerful investigative tool. And for me personally, that is my preference. If you are trying to find a problem, then this is the system to use.
That's quite interesting. You made another comment earlier that has just got me thinking. One of the challenges that we identified with both the SIPs and the DCBG was the inability to measure the pipe condition at road crossings and so on, because you can't work through tar. And from what you've said, the PCM can be used even if the pipe is, quote, inaccessible for a soil contact survey technique. So you could measure whether it was under tar, even though we can't contact it.
Yes, absolutely. And perhaps the only situation where it would not really be possible would be pipelines that are placed under reinforced concrete, such as, for example, airport aprons. If you had a fuel pipeline under the airport apron is strongly reinforced concrete or heavily reinforced concrete, and that would mask and interfere with the signal that is being measured by the magnetometer of the PCM detector. Other than that, it'll measure through rock, it'll measure through tar, it'll measure under ordinary paving, and so on, where your contact methods, the SIPs and DCVG, anything where you've got to measure potential and it relies on electrical contact with the ground, that has that limitation.
Interesting. Neil, obviously you've referenced an example where you would place the current source at, for example, a transformer rectifier, but is there merit in using the PCM where there's no cathodic protection? Can it be used if there's no cathodic protection?
Well, my question back to you is, if you haven't got cathodic protection, why are you worried about where the current goes?
Okay, blunt question.
These surveys are often done during pipeline construction with a view to the installation of future cathodic protection systems. So it's not only an investigative tool. And in that situation, you would want to know that your pipeline is ready for cathodic protection. So yes, you can use these if there's no cathodic protection, because you can take any point on a pipeline. You don't have to use a cathodic protection injection point. You can use a valve station or a terminal point or anything like that to inject the signal, and you just need a temporary earth point for the other part of the circuit. But the other really, really useful part of this survey technique is that it is really good at pinpointing the location of services, possibly more so than the conventional relatively high frequency metal detectors, because the low frequency signal is not induced from one system to another to the same extent that it is with higher frequency systems. The lower the frequency, the less the mutual induction between parallel points. So not only can you pinpoint systems, but you can also tell whether there is perhaps a contact between two pipes, because you then get a reversal in the direction of current flow. So if you had two pipelines parallel to each other and you inject the signal on the one pipeline, and you find that the signal is traveling in the opposite direction on the one next to it, you've got a pretty good indication that somewhere along that system is an electrical short circuit, which could be a mechanical interconnection, or of course it could be an accidental contact. But to illustrate the precision of pipeline tracing, I just want to show you an interesting example here. The image on the left is a general pipeline route map, which has been blown up to the same magnification as the one on the right. And it's got to the point that the image is so pixelated, you actually can't see what on earth is going on, because this here on the left is actually a bundle of pipes, all running in the same direction. And when we look at the image on the right, which is the detailed pinpointing of these individual pipelines using the PCM equipment, you can not only tell exactly where these lines are, and the separation of those lines is probably 0.5 meter, and the arrangement of the lines changes as they go through this corner, and you can see exactly where those pipelines are. Now, this is a two-dimensional image taken from the surface of the ground, but the advantage, another aspect of the PCM they haven't even spoken about, is that it also measures the depth of the pipeline below the surface. So you can then not only tell where the pipelines are relative to each other in the X and Y planes, but also you have a measure of the depth. So you can see, for example, where these pipelines cross, you can tell which ones are on top and which ones are underneath.
That is really, really useful, I'm sure, and possibly something that we don't use as often as we could. Neil, how sensitive is this to operator competence? Is this something that I could do with my clean shoes, as I call them? Or do you need to be really experienced before you can do these surveys?
Experienced in order to do the surveys? Perhaps not. I mean, you could go and do the survey. You can walk along a route and you can find the location of the pipe and you can press the button and get a reading and you will land up with some data. And I think the challenge is that if you start finding current going in different directions, you then need to know what you're doing in terms of how to deal with that situation. For me, the biggest challenge comes in what do you do with the data? This illustrates the sort of challenge that one faces. So again, thanks to Radio Detection's brochure for this example, where this is a plot of some real data on a pipeline with each point representing a PCM measurement in terms of the current intensity. And as you can see, it is not a nice, clean, simple graph that says, well, here's a problem and there's a problem and here the pipeline loses current. And so to interpret this data requires a lot of experience and knowledge on what it really means. And in this particular example, we have two typical defects, and you can see it's not a simple change. And that's because the equipment is a very, very sensitive magnetometer. It is sensitive to variations in the magnetic field that may be caused by other things, such as cable lying over the top of the pipe. May not be physically or electrically touching it, but it interferes with the magnetic field. You may have something like this point A here, where there appears to be a major point of interference, but actually it's not significant in terms of pipeline coating damage or signal attenuation. So yes, you really have to know what you're doing. And the use of this equipment is challenging, and you need to work in significant detail to be able to make sense. Also, you need to know what you are doing so that you can inject the signal at the right place in order to get the results that you're after. So like everything else, the equipment is only as good as the operator. But yes, it is a very, very sensitive piece of equipment, and it does sometimes give you what appear to be false indications if you don't know how to interpret the data.
So it's more the interpretation that needs a lot of thought behind it, like many techniques. Neil, we've had a question come in, which I'm not sure if it has been answered by the graph you've just shown us. And the question is, do we get a permanent record of the survey? And if not, how would we record our findings? Now, from that graph, it looks like it might be a permanent record.
Unlike, say, for example, the SIP survey, the equipment does not continuously record the data. So you would go to a point, you would find the exact center line of the pipe, get the equipment stable, and take a measurement at that point. And that measurement is then stored in the equipment. And with the more modern equipment than what you saw in the photograph, the equipment actually has built-in GPS engines which record the GPS location at the same time. On the older equipment that doesn't have that, you would have to carry a GPS with you as well in order to actually get that data. But you can store a significant number of data points in the equipment, which you then download, but it's up to you to then, depending on the age of your equipment, to interpret the data points relative to position.
Right, thank you. So would I then be correct to say that the PCM or internal current mapping technique is just an really excellent tool for tracing where our current is flowing? And we could possibly identify current drains on our network and use it to do quick overview survey to see where we might need to do something more intensive like a DCBG.
Yes, that's correct. And in fact, the PCM equipment as it is supplied by radio detection includes the facility to do that more intensive investigation work, which in the case of this equipment is then an ACVG, alternating current voltage gradient. But that again, just like with ECVG, requires contact. And so you have reference electrodes in the ground and you measure the gradients just like we did with ECVG. And that's the subject for tomorrow's discussion.
Right, so let's not get ahead of ourselves. Well, I hope that today has been helpful to our audience and clarified the technique to some extent. Thank you so much and enjoy the rest of your afternoon.